Okay, I want to give two simple examples. So, first is this Feynman diagram. So, I have a 4-point vertex here and a 4-point vertex here. So, clearly this is from 5-4 theory. So, this is a 4-point function, and I am interested in looking at g tilde 4. So, this is 4-point function and I am in Fourier space, that is what I specify by writing g tilde, and the external momenta are p1, p2, p3 and p4. Okay, so this is p1, p2, p3, p4. Okay, and as you can see that this is an order lambda cube diagram. One vertex is here, so that gives you order factor of lambda, and two vertices here, so that is lambda cube. Okay, and I want to write down the expression for this Feynman diagram. So, this is easy. First, let us use momentum conservation at each vertex and determine how many undetermined loop momenta we have. Okay. So, first momentum conservation at each vertex. Okay. So, p1 plus p2, that is coming in at this vertex, and you cannot determine the momentum that will flow through both these lines. So, let us say k1 flows through this and k2 flows through that. Okay. So, we just say okay, we do not know what it will come out to be, and I will just give them name and then determine using momentum conservation. So, let me first assign a momenta to each propagator. Okay, that is what I am doing. Let us say k3 comes in here, it flows like that, and k4 flows through this propagator like this. Okay. Let us call this vertex 1, this one as vertex 2, this one is vertex 3. So, at vertex 1 we have p1 plus p2, these are external momenta, and k1 and k2 are external momenta which are leaving the vertex. So, minus k1 and minus k2 are entering the vertex, and that sum should be 0. Okay, that is what you get from momentum conservation, which means that k2 I can write in terms of p1, p2 and k1. So, k2 is k1 k2 is p1 plus p2 minus k1. Okay. So, this one is now determined in terms of these remaining 3. That is good. Let us look at what happens at vertex 2. At vertex 2 you have p3 coming in, okay, k1 coming in, k3 leaving out, which means minus k3 entering that vertex, k4 coming out. So, again minus k4 entering in that vertex, and that sums to 0. Okay. Sum of all the momenta entering or exiting a vertex has to be 0. That is what momentum conservation is. And from this, as before, you can write down k4 as p3 plus k1 minus k3. Okay. Good. So, we have k4. Okay. So, let us see what has happened. We have apart from the external momenta, we have k1, k2, k3 and k4, of which we have been able to express k2 in terms of k1, okay, and k4 in terms of again k1 and k3. So, you see you have two momenta k1 and k3 which are undetermined, which are not fixed by momentum conservation. Okay. So, good. So, there is nothing that you can do about this. So, they will be there in the problem. Okay. So, now what we can do is we just write down the expression of this diagram and then discuss about it. So, we have run out of space here, but let me squeeze it in here. So, expression of the diagram. So, first factor, let us put the overall energy momentum conserving delta function that you know you will get, which is P1 plus P2 plus P3 plus P4 equal to 0. So, that is what this imposes. Okay. Then you have 1, 2, 3 this propagator and 4 propagators which do not involve momenta k1 and k3, they involve only the external momenta, and those I can write down. So, I have product I equal to 1 to 4 pi square minus m square plus I epsilon. Okay, so, I have taken care of these 4 propagators. Then you have order lambda cube expression. So, you will have minus I lambda over 4 factorial cube, and this is lambda cube. So, it comes with the 1 over 3 factorial and then I should multiply with the combinatoric factor. Let me write down that thing here. And this is an exercise for you to do, find the factor which you should multiply. And I should just point out here that in books, in several books, you will find usually that the vertex is chosen as minus I lambda rather than minus lambda over 4 factorial, and then the counting becomes different, but we will follow this way. Okay. So, we just keep the vertex as minus I lambda over 4 factorial, and then we just count the number of ways in which you get the same diagram, okay, without worrying about symmetry factors and other things. This will be simple. So, anyhow, then we have still these propagators 1, 2, 3 and 4, and for all of these we still have to include the momentum integrals. Okay. So, what I will do now is I will rename the momenta. So, instead of calling k1 I will call it q1, and k3 I will call it q2. Okay. So, this is q1 now and this is q2 now. So, d4 q1 over 2 pi to the 4, d4 q2 over 2 pi to the 4, okay. And then we have the propagators. So, I over this one will give you q square, q1 square minus m square plus I epsilon. This one will give you I over q2 square minus m square plus I epsilon, and this one is p1 plus p2 minus q1, right. K1 is q1 now, p1 plus p2 minus q1 whole square minus m square plus I epsilon, and the last factor is I over this is for k4. So, you have p3 minus q1 minus q2 whole squared minus m square plus I epsilon. Okay. So, that is the expression of this, and I hope you remember that all the other integrals over k4, k3, k2, k1, all the others have been already used up. So, at this stage the Feynman rule was you have to include only those integrals over only those momenta which are not which are left undetermined, right? All other ones have been used up when using and they have used up the delta functions at the vertices. Okay. So, this is the simplified version of Feynman rules which we have used here. And so, you see that this is a two loop integral or two loop Feynman diagram, because you have two undetermined loop momenta. Okay. So, these momenta k1, k3, or now what we are calling as q1 and q2, they are called undetermined loop momenta. Okay. And as you see that these run from minus infinity to plus infinity. Okay. And clearly, because these integrals, let me write them like this. So, d for q1 is basically dq10, dq11, dq12, dq13. So, these are basically x, y and z components, and this is the temporal component of the loop momenta. Okay. And they take all possible values, which means that q1 square minus m square equal to 0 will not be in general satisfied by this, right, because this is a very specific demand. That this says that q10, the time component, minus q11 should be equal to m square, right. But here these are completely unconstrained, they take all possible values. So, there will be many configurations of these momenta for which this will not be satisfied. Okay. And there will be of course some configurations for which this will also be satisfied, right, because they take all possible values. Now, when this is true, we say that q1 is on shell or on the mass shell. Okay. This is what gives you the mass shell condition. Okay. This is called as mass shell condition. So, if your momentum that is flowing through the propagator, if the square of it gives you, and by the square I mean this, square of it gives you m square, okay, then it is on shell. Otherwise, if this is not true, then we say the momentum is off shell or off the mass shell. Okay. That is just name for saying whether this condition is satisfied or not. So, you see that the loop momenta, when you are integrating, the loop momenta take off shell values, and of course, some of the configurations of the loop momenta will also be on shell, but a majority of them, or the largest chunk of it, is basically off shell. Okay. So, that is I think what I wanted to say about this diagram. And I mean, right now we are not trying to interpret anything as particles here, because we have just taken these as some green functions and or Fourier transform of these. But eventually in the next course, when we start talking about S matrix, you will see that these can be interpreted as particles which are moving in space and time, and they are interacting at vertices. But that interpretation we will save for later, and at this stage we just look at these as mathematical objects that we are trying to calculate. But when we do that interpretation, there you will be able to see that these will correspond to real particles, real meaning on the mass shell. So, these are really relativistic particles which are satisfying the on shell condition. So, they are real particles or on shell particles. But these ones, these propagators, okay, these will correspond to particles which are off the mass shell, which means they are called, that is why they are called virtual particles. Okay. So, this is for later, but just to tell you this. So, you say virtual particles and real particles and virtual particle is the one whose momentum, let us say if it has a momentum q, and if it is supposed to correspond to a particle of mass m, then q square is not equal to m square. So, that is a virtual particle, and if q square is equal to m square, then that is a real particle. Okay. But you do not have to worry about the particle interpretation at this stage. Okay, let me give you one more very simple example of another Feynman diagram, and we will write the expression for that one also, which the point that I want to make in this next example is that unlike here where you have many propagators and you got a loop diagram which is 2 loop. So, you might imagine that having lots of propagators will make it a higher loop thing, but not necessarily so, and we can think of a simple diagram which is one loop, but has many propagators, and we can easily write down the expression. Okay. So, because we are in 5-4 theory, we should have vertices which have 4 legs coming out from the vertex. So, 4. So, at each such point you have these. Okay. So, let us say this is P 1 which enters in here, this is P 2 which enters in there, and P 3, P 4 and so forth, and then you come to P 2 n, P 2 n minus 1. Okay. I could have put P n, but I am putting P 2 n because we are in 5-4 theory, and you can check that if you have odd number of phi's in the Green's function, then that it vanishes. Okay. That you will be able to check very easily. So, if you try to draw such diagrams, you will never be able to connect all the vertices and external lines if you have odd number of external lines. Maybe I will show you one after I finish this diagram. Okay, so let us see what it looks like. So, as before, we will assign momentum to each of the propagators. So, external ones are okay. So, let us start from here, let us call it L, and it flows like this, and then I should put something here, but then I realize I do not have to, because this one is completely fixed. So, P 1 enters at the vertex, P 2 enters at the vertex, L enters into the vertex, and that is what it has to come out because of momentum conservation at that vertex. So, you have here P 1 plus P 2 plus L flowing in this line. Similarly, here you will have, maybe I write here, P 1 plus P 2 plus P 3 plus P 4 plus L flowing in this one. So, you see it will always be, the undetermined momenta will always be L, which is in these. So, it is clearly only one loop diagram, and I think I will leave it as an exercise to write the full expression of this. I will just write the loop integral part. Okay. So, you put all the other factors and external propagators, everything, find the combinatoric factor, but as far as loop integral is concerned, this is what we have. Okay, again this propagator will be mostly off shell, this one, because you are integrating over L. Okay, all possible configurations are allowed. Okay. And then you will eventually have this one, which you can write in different ways, but so I will just write this one. minus, and of course, you can use momentum conservation at this vertex to write this piece as involving momentum these two, right, because this plus this plus this plus, so let's say this is called this one, let me call it k for a moment. So, you have P 2 n plus P 2 n minus 1 minus L, that is what enters in this vertex, plus k should be equal to 0. So, k is simply minus P 2 n minus P 2 n minus 1 plus L. Okay. So, that is what you can put in here instead of this fact what I have written. Okay. So, that is the loop momentum integral that will be here, and clearly this is a one loop diagram. So, if you have a complicated diagram and you are unsure what is the loop order, this is how you can do. You just assign momenta and use momentum conservation delta function at each vertex, and then you can fix or figure out which ones are undetermined. Okay. So, that is another example, and I just said let me say about the odd number diagrams with odd numbers of external lines, or equivalently Green's functions which involve odd number of fields here. Okay. So, let us call phi 1 to phi 2 n plus 1. Okay. So, this will always be odd number. So, let us see why you will get 0, and the consequence, I mean this is the consequence of phi going to minus phi symmetry. Okay. So, if you change phi by minus phi, things should not change, and that is what reflects into telling that if you have an odd number of fields in the Green's function, that vanishes. But let us see that at the Feynman diagram level. So, suppose you are looking at a 3-point function. So, at each external point you remember you get one tick, and suppose you are looking at at one loop, sorry, at order lambda or at order lambda. So, when you have order lambda, you have this vertex. Okay. So, you can contract this with that, this with that, this with that, and 1 remains. Okay. And which means that because this is uncontracted, this vanishes. So, let me remind you why this vanishes. Remember that when we were looking at the time order product of the fields, this is what everything had boiled down to when we were trying to write down this expression, and there if we turn this into normal order product, right, and that helped because once you have everything normal ordered and you have vacuum on left and right, only those terms survive which are fully contracted, right. We were contracting, we had several fields here and we were contracting this. So, you see that if you have odd number of them, one will always remain uncontracted, okay, and that uncontracted one will kill the vacuum, that is what is going to give you 0, because that will kill the vacuum. Okay. These are complex numbers, so they were fine, but the one which will be left, it will be an operator and it will kill the vacuum both on the left and right, and it will give you 0. Okay. So, that is the reason why if you have odd number of external lines in phi 4 theory, you will get 0. But if you are looking at phi cube theory, where the interaction term had a phi cube, then you will have a vertex, let us say g phi cube, then you will have a vertex minus I g phi cube, minus I g, okay. And then you can construct in that theory Green's functions with odd number of external lines or external points, because this you can then connect, right. This is not vanishing, this is fine, and I will ask you to convince yourself that this is a consequence of this symmetry which you are seeing here. Okay, good then. So, I believe that you have now some more experience of writing down expressions for Feynman diagrams and what loop momenta are, and why, as you will see later, these particles which are virtual particles. Why they are called virtual particles if they are running in the loops, okay, because they are off the mass shell. Good, then, so let us meet in the next video.